So there's an exam on Monday. There it is, exam 2. It covers everything, up to and including sorting. Here's some example problems. And but there'll be other kinds of problems, all kinds of problems, everything. The questions on the Unix command line, and reading code, figuring out what it does, implementing functions with vectors and arrays, sorting, searching, binary search, linear search. Any questions about the exam? Yeah.
So will it cover also like some things that we did on exam 1?
One more time, say it again.
Will it also cover like the previous?
Yes, previous. It will cover everything that we've done already, all the way back to day 1. So for instance, there will be questions about the Unix command line, like ls, pwd, you need that, okay? As an example, it goes that far back. So it's cumulative. So we have 2 more topics to talk about. So today we can get classes done. So we'll just dive into that. No, I don't need to look at that. What do I have here? So I have some examples. This is a point class. And what we can do here is talk about classes now. All right. Nothing there. Okay. Let's just make a file and start illustrating this this thing called a class. A class is a user-defined data type. So it's like an int is a data type. So we go int x, we create an instance of x. Or string y, we created an instance of the string data type and name it y, that instance. So you've got data types, and then you have instances of data types. So a class is a data type that the user defines, or it could be pre-supplied by the compiler as well. Well, there are classes that are specified for the C++ language, like vector is a class, string is a class. Those are actually classes. So we're going to learn about how to define our own classes and use them. So I'll just set this up quickly. Okay, that works. All right, so let's define our own class, and I'll use that example from the lecture notes. So there's a class called point, and instances of this data type will represent points in 2 dimensions. So you define it like this. You start with the word class, followed by the name of the class, name of the data type. Open, close braces, and you need a semicolon right there. That's important. So this will probably compile. Of course, it doesn't do anything, but that's syntax is good. If we leave out that semicolon, it won't compile. You see that? Actually, it's a common mistake, so the compiler can look for that. And so the class is like, just like this vector class, the string class, it has operations. And let's see what operations I have in there. I haven't done this class here. I'll like get, set, distance from, okay. So there's a section of definitions of functions and variables that are visible to code outside of the class. And we start that section with this keyword public. And then there's another section called private. That's to hide things. And normally what we do is we hide the primitive data types that our class is based on. For instance, for a point class, we might have two doubles, say call them X and Y, to represent a location in 2 dimensions. So it's a point in a 2-dimensional plane. We have the XY coordinates. That's what we're going to represent. But let's get rid of this private section. Let's suppose we make these public, like this. So this is a pretty simple class. We create an instance of the class like this. Notice by convention, we use an uppercase letter for the class name. But for instances of the class, we'll by convention use a lowercase letter. It's not required by the compiler, but it's a general convention that programmers follow. So this creates a point, but now this data type, this instance here, point, I'll call it PT, how's that? That's better. This, or just P. The point P is an instance. It needs memory to store its state. And its state is comprised of these two doubles, X and Y, that's it. And we can create any number of these instances. So there's P1 and there's say P2. And when we create P1, we can access its member variable X with a dot notation. P1 dot X. Let's set that equal to 3. P1 dot Y. Let's set that equal to 4. So you can imagine what that looks like on the graph. You know, position 3, 4. And P2 just for fun, maybe a little more than fun, I'll set that to the opposite, -3, -4.
Under P2, would you also want this?
Oh, yeah, thanks. I forgot that. Yeah, that should be P2. Thank you. So let's think about what we want to do here. Well, P1, this point, let's suppose we want to know the distance from P1, from the origin to P1. What's it going to be? I'll call it D. Look at that. It's the distance right there. Or maybe because I typed the word distance in there. I don't know. So the distance from the origin to P1 is the what's the square root of P1 dot x times P1 dot x plus P1 dot y times P1 dot y. That's the distance formula. I think I got that right. Yeah. And so we print that. Let's see how that works. P1.y not declared in the scope. Let's see, this is P1. Oh, square root is not defined, sorry. So we need C math to define square root. So we run this, we get 5. That's because it's a 3, 4, 5 right triangle. So that's why I did that. I picked 3 and 4 to get that number. The distance from origin to P1 is 5. And let's suppose that we want to do the same thing for P2. And I'll call it, say, D2. This is D1. D1 and D2. The distance from origin to P2. Five and 5. Maybe that's not too interesting, is it? How about make this -1 and 3. It's almost pi. So let's suppose we had a lot of points to do this with. Well, we don't want to just copy this formula over and over again. We want a function. So we might define a function. Call it distance from origin. And we're going to take a point P. And we don't need to modify P when we get it in this function, so we can declare it as const reference. Const means we're not going to modify the data in P. Reference means don't make a copy of the point. Just let me have a reference to the point data in the calling that the calling code has access to. So that's for efficiency. Don't make a copy. Just give me a reference. And then we use this formula here. We don't need to save it in a variable. We'll just return it straight away. and this is P. Because in the function is generic, so we don't need a P1 or a P2 there, just P is good enough. So now, we'll just call this function. Distance from the origin, P1. Like we don't need this duplicate code here. So we're deleting duplicate code. And we're removing a variable, D1 and D2. Distance from origin, P2. See how nice that is? Makes the code look a lot easier. It's smaller, easier to read. The same values. But now with classes, normally we don't do it like this. This is an external function. This is just defined only to work with points. So what we do normally is we put it inside the point class. So we put it in here. And now it becomes what's called a member function. So we can't call it we call it a little differently now. We don't take an argument. We don't need to take this argument now because we're associating it with points. And so we don't pass in an argument. Actually, there's an implied argument because we invoke the function using this dot notation. So the object, the reference here, this object, this variable refers to the object. It's an implied argument in the function. And this is what it looks like. P was not declared in the scope. Where is that? Oh, sorry, of course. We just have access to X and Y here. Yeah, see, we're not naming, it's just, this is an internal function. So we know our own state. We have access to it. So we just use those names directly here. We don't need to go through the dot operator. Same result. This is not a required format. We could put it up like this. Maybe we'll do that to see more stuff. And one other thing is this. This function, we want to declare this function as const. We do that right there. Because when we call distance from origin, we don't modify X or Y. So we tell the compiler that this function does not modify X or Y. What if we tried to modify X? All right, because we said it was const, the compiler will say, nope, can't do it. See, error, assignment of member X in read-only object. So read-only object. So, well, we could take the const out. It'll compile now. But the code is not correct, of course. We're modifying X. We don't want to do that. And how did this change here? Oh, these both changed because modified X. So we want the const in there because it reveals a bug. in this case. It reveals a logic error. And so we solve the problem not by removing const x, but by taking out the logic error. And let's suppose instead of distance from origin, we wanted to know the distance from P1 to P2. The distance from P1 to P2, that's what we want to say, okay? Well, I'm going to see, I'll do in the test code, I'll write what I want the test code to look like, and then we'll go to the class and see how to implement it. So the distance from P1 to P2, so we'll go P1, distance, I could do, it doesn't matter, but I'll do it like this, P2 dot distance from P1. So I'm going to pass in this P1, this point here, because this function that is access to this dot operator on an object has access to that object's data, but doesn't have access to other objects' data. So if we want access to P1's data as well, we have to make that available through the function call. So it'll be distance from some other point P. The distance from P to us. The distance from point P to me, we can say like that. But we'll need to fix this distance formula. It's going to be P dot x minus x times P dot x minus x. So that's the difference between the x values in us, x, and the other point, P dot x. The distance between their x values squared. So we have to add that to y. The same thing with y. So that's the distance formula there. Let's test it. We better make sure we got that right. So if P2 were, say, 1, 1, and P1 were to be 4, 5, then I can see the distance would be 5, right? Because we make a line there, and the line will be the edge of a 3, 4, 5 right triangle. So this is the test code. So this should be a 5. Let's see. There it is, 5. What about a function that modifies the state of the point? Let's declare a function set x. So we want to set x to some value that we're passing in. Well, we want to take our x, that's part of our class instance, and set it to the value x that's being passed into the function. Well, we're using the name x 2 times, so we need to distinguish the x that lives inside the instance. We identify using this notation. And the x that represents data that's being passed into the function, we just use it straight away like this without having to add any annotation to it. By the way, this is a pointer. This is the memory address of the object. That's what this is. It's the byte address of the object in memory. And this thing that looks like this dash greater than symbol is a what do they call it? A dereferencing operator. So you can think of this as a reference. It's for dereferencing a member data for an object. Let's do the same thing for y. So now we're changing the state of x and y. We're passing in new x and y values. We cannot declare these as const. That'll fail because we wouldn't be able to modify x. So we can test that. Like, let's have some test code here. This should be 5. It's not good to do exact comparison with floating point numbers. So it makes me a little uncomfortable, but we'll leave it like that. In fact, I'm going to get rid of that. I don't like that. All right, so if we did p1 dot x and set it to 0, and sorry, p1 dot set x to 0, and then so if we set x to 0 and then y is just equal to 5, then the distance to the origin should be 5. So this should be 5. Got it. Now, one of the patterns that programmers follow is to hide the internal data to a class from the outside. So they would normally put these x and y values in a section declared as private. So if you want to set x, you can't just set it like this anymore. This is no good anymore. It'll fail to compile. We're going to pass it into the function setX. Oops, I messed that up. There it is. See? Point X is private. You can't do this. Y is private. You can't set P1.x to 4 because X is now declared as private. And this code inside main is outside of the point class. You can modify values in the point class, like here, if you're inside the point class. If you're implementing a function in the class itself, you can access the private member data. But if you're in main or anywhere else which is outside of the member functions, then you can't access private member data. So we would need to do the following. We would have to do P1.setX to 4. That's how we'd have to do it. And set Y to 5. And get rid of this. So just to show you, that's the old way to do it, and here's the new way. We pass it into a function. And same for this one. P2, set X to 1, set Y to 1. Now we're back to where we started from. Everything is good. Now what about this thing here? When we create an instance of this point, we actually don't normally do it like this. Normally, we pass the values in when we create the instance. We do it like that. It looks like a function call. We're saying, I want an instance of the point class called P1, and I want to pass in the initial values, 4 and 5, for the X and Y coordinates. That's called a constructor. A constructor is a function that runs when an instance of a class is created. Let's define the constructor here. Constructors are functions that have no return type, but their name must be the same name as the class. And they take between 0 or any number of arguments. Now what do we do with, and it's a function, so we have we have this area to run code in. What we do with the X and the Y is we use them to initialize our member variables. So this X gets the X, it's just like this function down here. See it? And this Y gets Y. So when the constructor runs, down here we create an instance of the object. And this is the standard notation. It's just like doing int k equals 3. This is just very similar. In fact, you could do it like this. This is acceptable. So you have the data type here, and the variable name, and then the data that's being used in the initialization process. It's the same thing. The data type, point, the variable name, and the data that's being used for the initialization activity. we do the same thing with P2. You can see that the code is getting smaller. It's getting easier to read. So I can quickly see I got a mistake. You know, the whole point, this is not, you don't need this to solve any computing problem. You don't need classes. You need loops. You need if statements. Have to have those. If you don't have those, you can't solve certain problems. So you don't need classes. But we use them because it increases the readability of code. And code can become very hard to read when the number of lines gets large. And we're talking programs that have millions of lines of code. Those are big programs. An operating system like Windows has so many, 10 million lines of code, something like that. Last I heard, it goes up every year. And but even if your system is smaller, maybe you have 30,000 lines of code. I mean, that's a lot of code, right? So you need tricks, you need techniques to impose some kind of organization on that code so that you know how to find things. You know how to change things. You know how to attach new functionality. So the code has to talk to you. It's got to be readable. You know, otherwise, you'll just get lost. So this is these user-defined data types, or they're also called complex data types. Complex because they're generally made up of instances of primitive data types. So we say complex data type. But these things are used to improve readability. Now, one more thing about the constructor. This is one style, and then there's another style, which I would say is more efficient. And that is we use an initialization list in that location right there. Oh, you need a colon here. You have a colon, so you have the declaration, you have the constructor name, the parameter list, a colon, followed by how the member variables should be initialized. So x should be set to x. And this x here that I have highlighted refers to the member variable x. And this x here, that x refers to the parameter x that's being passed in. So we use the same name because, you know, that's where the x that's being passed in, it's destined to go into the member variable x. So it's like good documentation to use the same name. But you'll see in a lot of beginner textbooks, they're going to change the names, because this is easier for, in those authors' opinions, that this is easier to understand conceptually. But that's not what you see in practice. Well, sometimes you do, but in a minority of code. In the majority of code, you'll see the same values. But you can do it like this if it helps you, because if this is the first time you've seen this, this should be very difficult to understand. This is very difficult to get. And I say that not because I know it's difficult, but because I teach this class every quarter and everybody struggles with this. But I also know it's difficult because actually in the field of computer programming, or computer science, we'll say, that when classes or user-defined data types were first introduced, they didn't become popular overnight. In fact, there was a lot of resistance to using them. It was thought to be, too confusing, not helpful for readability, and it was almost like a war. They had a war for decades. I mean, not just a couple of years, but tens of years. There was a war about this. And you had, it's like Republicans and Democrats. They just hate each other. They just see the world differently. But the thing is that the war is over. It's totally over. Totally over. Well, not totally, but it's pretty much totally over. And classes are ruling right now. Any new language that comes out has classes in it. Any old language that's being used heavily, normally, it's modified to support classes. It could be an example. Python. Python did not originally have classes, but now it does. PHP, it's a web development language, did not originally have classes. Now it does. Those are two big examples. The C language became C++ mainly through the addition of classes. So C does not have classes, but C has evolved into C++. And all the other big languages, Java, C#, you just name it. They're called object-oriented. It's a style of programming called object-oriented programming. So I'll just see if I have any errors here. What is going on? I must have been hitting some buttons. What else do I want to do here? Usually, if you have a set, these are called setters. Normally, if you have setters, you also have getters. So you want to get x, and that would be const. Simply return x. Same thing for get y, except I need to spell that right. So we might want to test those. What should that print? 5, right? Should print 5. So we're always printing 5 over and over again. Here we go. Prints 5. So that's pretty much a complete class. So one other thing I wanted to show you is it's called the UML class diagram. And we have a few minutes. There's a standard way of showing the organization of a class. It's called the class diagram, which is a part of this specification called Unified Modeling Language, or UML. So I'm going to just, normally you use some kind of automated drawing tool for this, but I'm going to do it the old-fashioned way, just use characters. So we have 3 areas. The middle area is the class name. And the second area contains the member variables. We use a minus sign to indicate that they're private. So we have a member variable x, which is of type double. Maybe I'll put a space there. So, you know, this editor is mixing tabs with spaces, so this is not a good idea, but I don't know how to turn that off right now. This is y, that's also a double. So you have the name of the variable, a colon, followed by the data type. It's the same with the functions. And these are public, so I'm going to use a plus sign. We have the constructor, and I guess there's different ways of doing that. I'll do it like this. And then we have the maybe the getters and the setters. So we have getX. And getX has a return type of double. And y has a return type of double. And set x takes a value x of type double. And it has no return type. I'm just going to leave that off. I'm not going to show void or anything like that. And then set y. And then we have distance from origin, distance and distance from. So distance from origin. And that returns a double. And distance from. And that takes another point, say P, of type point. And that returns a double. This is just the syntax. Some people, you know, love these things, and this is critical to their projects. And others don't use them very much, like me. I just don't use these so much. Some people, they go really far. They actually use tools that generate code from UML diagrams. It doesn't generate all the code, but it generates like the skeleton of the code, and then you provide the implementation details. So there's some automated code generation tied to these in some cases, but generally they're used just for documentation, just to get a bird's eye view of a class and say, oh, that's what's in the class, that's what it looks like. And I do believe these used to be more popular than they are these days, but nevertheless, this is on the list of things I need to teach, and it is useful. I mean, certainly. If you want to get into this field, you need to know how to read a UML class diagram, absolutely, for sure. Whether you use it yourself in your own work, that's another case. Yeah?
Does the compiler know that that's a UML diagram, or do you have to comment that out?
Oh, it has to be commented, and I didn't do that, so I made a mistake. Thank you. This should be just a comment. Thank you very much. Let me make sure I didn't break it. Looks okay. Here we go. other thing that also these classes can be, I should probably go one step more here. These implementations, these are called inline implementations. But typically, you don't have all inline implementations. You'll implement the class implement a function outside of the class. And I want to show you how to do that. So the class itself would not have the implementation. That means it would not have the instructions inside the curly braces. It just has a declaration like that. The name, the type that parameters that it takes, if it's const or not, and the return type, double in this case. And then outside the class, we provide the implementation. And here we need to tell the compiler that that distance from origin is part of the point class. So we use this method to make that identification. So we use this two colons preceded by the name of the class. That's a prefix to the function name. So once again, up here, in this declaration block, we don't have the implementation details for the function. And we implement the function later on down here. Let's see if we got this right. We did. Works. And so we'll do that for all of these. And then this looks like that. See, we're making this declaration here, we're making this smaller and simpler. So for this class, this is all right. You could do it either way. The first way I showed you, all inline, or you could have some inline, like these are still inline here. Some inline, some external, or everything external. You could do it that way, including the constructor. So that's your choice. So in this class, that's good enough. But of course, there's a little more there in real life. If the class is simple and small, this is okay. But if the class is large, you've got too much to read in this file, so you want to separate it out into another file. I'll show you how to do that just for the record, but you don't need to do that in this class. Okay. I'm going to copy main to point.h. I'm going to copy it to CPP. Now, we're going to simplify main. We're going to get rid of all this code. See, it's nice to have nice, simple files, right? We just want the test code in this file. Now we'll need an include statement. We have to include point.h, the header file for the point class. So we don't use angle brackets there. Angle brackets are for headers that are provided by the system. But for user-defined header files, we use quotes. And let's see, what does that header file look like? Well, the header file looks like this. We could say leave the UML class diagram in there. We can do that. The header file just has this section right there. The class declaration and any inline functions. But it does not include the external function definitions. Of course, we don't want main in there either. So here's the header file. Now these header files, they can include other header files, and those header files include other header files. Sometimes you get cycles when you do including header files. So you want to tell the compiler to not to, to break a cycle, only include this once. And the modern way to do that is just to type that in there, pragma once. That's the modern way to do it. But you might see old code that does it a little differently. It's, if endef, if not defined, that's a pre-compilation directive. If not defined, point underscore h, then define point underscore h and close it down here. End if. That's called a, what do they call that? Forgot the name, something guard. Define guard, something like that. So if point.h is not yet defined, well then define it and then also include all this business. Then the next time the compiler tries to include the file, it'll get to this directive. If not defined, oh, but it is defined because we already included the file once before. So now we defined it. So so we only do this block in here if point h is undefined. But now that it's defined, that's why we avoid cycling, by recursively including one after another in some kind of a cycle. But once again, that's the old way to do it. You'll see old programs that use that. But the new ones might just use pragma once here. That's now widely supported. For this class, you don't have to remember this, but if you go on in this subject, you'll get hit with that. Now the point class, we don't need what's in the header. We don't want to duplicate code. So the point.cpp, that's the implementation file. It's just the functions that are defined externally. That's point.cpp. Now we need to include the point header file. We need to know, the compiler needs to know how the point class is declared. And now, when we compile this thing, it's not good enough just to list main.cpp anymore. Now we need to list all the CPP files, main.cpp and point.cpp, but not the header file, because that comes in through the include directive. The include directive tells the compiler to go open that file, copy its contents in at some point in the code. But it doesn't know to load and compile the CPP files, so those are listed all on the command line in this case. And we got a problem there. This was not declared in this scope. All right, distance from origin, square root not declared. Oh, that's easy. Actually, main does not use square root at all. So in fact, we don't need cmath in main. We needed cmath to get the square root, which we use in this point.cpp file, so we'll include it there. Now it compiles, now it runs. So that's the normal organization. You have code that uses a class. They need to include the header file. The header file has a declaration of the class in it. Normally, it doesn't have a UML diagram, but we're doing that here. This is normally what's in there. It has inline implementations here. And then there's a third file which has the function definitions in it, which also must include the header file for the class. And that is it. That's a big overview. Now, there's other topics. This gets crazier. You have things called subclasses. And No, mainly that's what it is, subclasses and interfaces. And you'll get that next quarter if you take the next class, 202. But this is all I want to talk about. Let's see, where are we here? A minute. So, is that enough for you? Actually, this is always, what do you call it? Overloading. So you should be totally overloaded. Am I right? Are you totally overloaded here? Well, if you're going to go on, if you're not going to do any of this stuff ever again, you're not going to be a programmer. Or if you don't want to be involved in programming, then you don't need this. But if you're going to be involved in programming at all in your life, you have to know this. It's not that you have to know C++. You have to understand the concept of classes, user-defined data types, how to define them. What is a constructor? They all have constructors. Getter and setter, public versus private, those access qualifiers, they all have this. And so this is a common pattern that appears everywhere. So it's important, but like I said, if it wasn't so hard, there wouldn't be a 20-year religious war over this, okay? I'm telling you, it was a serious war, decades long, because it's hard to get over, to break through the ice and to get a handle for this and get comfortable with it. But now that war's over, and this is how they do it. Although some people are trying to think of ways around it, and it might be in the future that this might be the old way to do things. But right now, this is pretty much universal. This is how code is organized these days. And once you get to do it, it's really natural. It's just super easy later on, of course. Everything is like that, right? All right, so that's it then. Okay, finished? Test, exam on Monday. Everybody ready? Or you will be ready. Question? Huh? Oh yeah, it's Monday, isn't it? I thought it was Wednesday. What am I doing? That's a week from today, right? Yeah, if you want to do a review on Wednesday, I'll do whatever you want to do on Wednesday. We'll do that. Yeah. Okay. All right. We'll see you.